James Webb Space Telescope, JWST, has been a beacon of hope for astronomers and space enthusiasts alike, with expectations soaring high regarding its potential discoveries. Humanity's insatiable curiosity about the universe's mysteries has driven scientific exploration for centuries. Since its launch in 2021, the JWST has been silently peering into the depths of space, capturing images that are revolutionizing our understanding of our place in the cosmos. In a recent jaw-dropping discovery, JWST found something so extraordinary that it defies the laws of physics, leaving scientists puzzled and uneasy. Are we alone in the universe, or are there hidden forces yet to be uncovered? Join us as we delve into the latest incredible discovery by the James Webb Space Telescope. Dark matter, a mysterious and invisible substance, has long been a subject of fascination and study for scientists. Though we cannot see it directly, we know of its existence because of the gravitational pull it exerts on visible matter. It's like a cosmic ghost, lurking in the shadows and affecting everything around it. Scientists estimate that dark matter makes up about 25% of the universe, a significant portion considering we can't even see it. This enigma has puzzled scientists since Fritz Zwicky first proposed its existence in 1933. It's challenging to study because it doesn't interact with regular matter in a way that we can easily detect. For years, scientists believed the universe was gradually slowing down. However, NASA's Hubble Space Telescope made a groundbreaking discovery: the universe is actually speeding up, a finding that turned the scientific community on its head. Around 95% of the universe comprises dark matter and dark energy, the invisible forces behind the scenes, orchestrating the cosmic dance while the stars take center stage. Enter the James Webb Space Telescope, the latest marvel in space technology. Equipped with a massive mirror and the ability to zoom in on distant celestial objects, the JWST is like a superhero gadget for astronomers studying dark matter. One of its remarkable capabilities is gravitational lensing. Imagine looking at a distant galaxy with another, closer galaxy bending the light in between, acting like a magnifying glass. By measuring the light's bend, scientists can estimate the amount of dark matter present around the closer galaxy. Researchers in Italy are leveraging the JWST to study ancient galaxies, some dating back 13 billion years. They are also using advanced computer simulations to understand the formation of the first galaxies. The composition of dark matter is still a topic of debate. While most scientists believe it is cold and interacts only through gravity, others propose it could be slightly warmer, with faster-moving particles. Dr. Umberto Maio, a researcher at the Italian National Institute of Astrophysics, highlights the invaluable insights gained from studying galaxies formed within the first billion years after the Big Bang. In a recent study published in Astronomy and Astrophysics, Dr. Maio and his team used JWST data and simulations to rule out certain dark matter models, narrowing down the possibilities of its composition. Their study stands out because it utilizes data from much earlier cosmic times than previous research, providing fresh perspectives on dark matter's properties. Dr. Maio explains that the mass of dark matter particles significantly influences the universe's structure, especially during the era of the first stars and galaxies. Different dark matter models lead to variations in star formation rates, ultraviolet luminosities, and molecular abundances. By comparing these variations with the latest JWST data, researchers are refining our understanding of dark matter. This research marks a significant milestone in our quest to comprehend the early universe. Observing the most distant galaxies grants scientists valuable insights into their composition and evolution. Dr. Maio believes that as more data becomes available, particularly about smaller and younger galaxies, we will uncover additional clues about early stellar formation and galaxy properties. The discovery of these early galaxies is remarkable because it demonstrates that complex structures can form rapidly on a cosmic timescale. This paves the way for future studies to delve deeper into the nature of matter and galaxy formation. As technology advances and more powerful telescopes become available, we can anticipate even more exciting discoveries that will further expand our understanding of the universe's origins. Alongside ongoing investigations into dark matter, another intriguing theory has been proposed by astrophysicist Jamie Farnes at Oxford University. Farnes suggests that dark matter and dark energy might coexist as a dark fluid composed of negative masses, a peculiar substance with negative gravity that repels objects instead of attracting them. Farn's theory, published in Astronomy and Astrophysics, seeks to explain the rapid rotation of galaxies without them tearing apart, thanks to the protective embrace of dark matter halos. According to this theory, a negative mass dark fluid could catalyze the formation of these protective halos. However, a challenge arises if dark energy diminishes over time, contrary to observations indicating its relative constancy. To address this, Farns proposes a matter creation theory, suggesting the continuous generation of new substances to replenish disappearing negative matter. He uses an analogy, envisioning spacetime as a bowl of popcorn, with negative masses popping into existence like kernels turning into fluffy popcorn. While Farns' dark fluid theory is captivating, it remains speculative, grounded in mathematical models and simulations. Farns himself is cautious, refraining from asserting it as a definitive explanation. Other scientists approach it with healthy skepticism, acknowledging that while the theory elucidates some aspects of the universe's behavior, it must satisfactorily address all observed phenomena. Geraint Lewis, a professor of astrophysics at the University of Sydney, emphasizes the need for extensive groundwork before accepting new theories. He points out that understanding negative mass and how it fits into our current knowledge of the universe is a significant challenge. To explore these questions, organizations like CERN are conducting experiments to investigate the possibility of negative masses, similar to those proposed by Farns. The Square Kilometre Array, the world's largest radio telescope currently in development, is another example of pushing the boundaries of fundamental physics. Lewis believes that these endeavors hold great potential, ultimately improving our everyday lives by deepening our understanding of the universe. Scientists have also presented another intriguing argument about the visible universe, which includes Earth, the Sun, stars, and galaxies. These are made up of protons, neutrons, and electrons, the building blocks of atoms. However, a mind-blowing revelation from the 20th century tells us that ordinary matter, also known as baryonic matter, constitutes less than 5% of the universe's mass. The rest comprises dark matter and dark energy, a mysterious force that seems to push objects away from each other, counteracting gravity. This realization opens up a vast realm of questions and possibilities in our quest to understand the cosmos. Most scientists are still trying to directly observe dark matter, a substance that doesn't interact with regular matter and remains invisible to light and other radiation forms. Despite our inability to spot it with current tools, we believe it's out there because it affects the motion of galaxies and galaxy clusters through its gravitational influence. Imagine a spinning spiral galaxy, stars near the center, where most of the galaxy's matter is concentrated, should move faster than those farther out. However, observations reveal that stars move at roughly the same speed regardless of their distance from the center. This discrepancy makes sense when we consider the presence of an invisible mass of dark matter around the galaxy, exerting a gravitational pull on the stars. Some scientists propose that we might need to rethink how gravity works to fully understand this phenomenon. Dark energy, even more mysterious, surprised scientists when they discovered its existence. Initially, they believed gravity would slow down the universe's expansion over time. However, measurements showed that the universe's expansion is accelerating. This unexpected finding is akin to throwing keys up in the air, expecting them to fall back down, only to see them shoot up toward the ceiling. Scientists now think this acceleration results from quantum fluctuations in space, creating a push that speeds up the universe's expansion over time. Albert Einstein's cosmological constant, a concept he introduced and later discarded, is being revisited. He proposed that this constant could act as a repulsive force counteracting gravity, preventing the universe from collapsing. Though he abandoned the idea when he learned the universe was expanding, dark energy has prompted scientists to revisit and investigate this concept further. Understanding why this mysterious force exists and its implications for the universe's fate is a major focus of modern cosmology. In 1915, amid the chaos of World War I, Albert Einstein introduced his groundbreaking theory of general relativity, revolutionizing our understanding of gravity and replacing Isaac Newton's long-standing ideas. By 1916, Einstein applied this new theory to the universe, concluding that it couldn't remain static, it had to be either expanding or contracting. This theoretical insight was confirmed in 1929 when American astronomer Edwin Hubble observed that galaxies were drifting apart, propelled by a colossal explosion. This observation provided evidence for the Big Bang, the moment when the universe began expanding.
Hubble's discovery implied that the space between galaxies was growing, indicating an expanding universe. Einstein's theory accommodates various models, including an infinitely stretching universe with no boundaries or a universe curving back on itself like a higher dimensional sphere. In the latter scenario, powerful telescopes could theoretically observe the same galaxies on opposite sides of the universe. Some scientists argue that the universe has an edge, not physically, but in terms of time and visibility. They point out that the universe began with the Big Bang approximately 13.8 billion years ago, meaning the farthest objects we can observe are those whose light has had enough time to reach us, 13.8 billion years. This distance forms the observable universe, a sphere with Earth at its center, stretched to a diameter of about 92 billion light-years due to the universe's expansion. Beyond this lies the cosmic horizon, similar to the horizon we see at sea. Just as there is more ocean beyond the sea horizon, we know there are countless galaxies beyond the cosmic horizon, whose light hasn't reached us yet. One of modern astronomy's pressing questions is whether the James Webb Space Telescope can see the universe's edge. The JWST, with its advanced technology, is designed to look deeper into space and further back in time than any previous telescope. It can detect the faintest and oldest light in the universe, potentially observing objects that existed just a few 100 million years after the Big Bang. While it won't see the universe's absolute edge, it will help us understand more about the early universe's formation and evolution. Spending $10 billion on a space telescope might seem extravagant, but the JWST's capabilities are unmatched. It is 100 times more powerful than the Hubble Space Telescope, capable of capturing faint infrared light from the first galaxies in the universe. It is also designed to study exoplanets and their atmospheres for signs of life. However, there is still uncertainty about what scientists will discover when they point the telescope toward the universe's edge. Understanding this requires knowledge of the observable and unobservable universe. The observable universe includes everything we can detect, but there's a limit to what we can observe. The farthest light we can see comes from the cosmic microwave background, which appeared about 13.8 billion years ago. At that time, the universe was like a thick fog, making it opaque. Some scientists think that gravitational waves and neutrinos might come from even further away, but we can't confirm this yet due to technological limitations. Cosmologists suggest that the observable universe is just a small part of a much larger reality. One of the farthest galaxies discovered, Aegis 2744y1, is notable for several reasons. Its light takes 13 billion years to reach us, meaning we see it as it was when the universe was about 650 million years old. The discovery involved 3 telescopes, Spitzer, Chandra, and Hubble, each working with different parts of the electromagnetic spectrum. Combining data from these telescopes allowed scientists to study galaxies much farther than any single telescope could manage alone. Spanish astronomers from the Instituto de Astrofísica de Canarias, IAC, and La Laguna University first detected the galaxy using Hubble, then measured the distance with Spitzer. They also estimated the number of stars in the galaxy. Gravitational lensing, a concept similar to a magnifying glass bending light, helped bring the images of distant galaxies into focus. Albert Einstein's general theory of relativity predicted this effect, allowing us to see the universe's most distant objects. Gravitational lensing occurs because the massive gravitational field of a closer galaxy bends the light from a more distant galaxy, magnifying it and making it visible to our telescopes. AL 2744y1, though small, is fascinating. Measuring about 2,300 light-years across, it is nearly 50 times smaller than our Milky Way. Despite its size, it excels in producing new stars at a rate 10 times faster than the Milky Way, characteristic of young galaxies in the early universe. Astronomers use the term redshift to describe how far light from a galaxy has traveled and shifted toward the red end of the spectrum due to the universe's expansion. AL 2744y1 has a redshift of 8, indicating its light has traveled for a very long time, almost to the point of the Big Bang. Before its discovery, the most distant known galaxy had a redshift of more than 7. From exploring the farthest galaxy ever captured in an image, we now turn to another distant marvel, the most distant supernova ever discovered. The record goes to a supernova named D6C2NM, found by the Dark Energy Survey, a project aimed at understanding the universe's accelerated expansion. Supernovae are powerful explosions marking the end of a star's life.
These stars, typically at least 5 times bigger than our Sun, meet their explosive end in a dramatic final act. Let's take a closer look at their life cycles. Stars are born from clouds of gas and dust in space. Over time, gravity pulls these clouds together, causing the material to collapse and form a star. In the core of this new star, nuclear fusion begins, generating energy that makes the star shine. For most of a star's life, it remains stable, balancing the outward pressure from nuclear fusion in its core with the inward pull of gravity. However, this balance can't last forever. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity's pull. The core collapses, and the outer layers fall inward, generating incredible heat and pressure. When the core can't be compressed further, it rebounds, sending shock waves through the star. These shock waves cause the outer layers to explode outward in a supernova. The energy released can outshine an entire galaxy for a short time, scattering the star's material into space, where it can eventually form new stars and planets. This process plays a crucial role in the cosmic cycle of matter and energy. The supernova D6C2NM, identified by the Dark Energy Survey, provides scientists with a fresh perspective on superluminous supernovae, rare and incredibly bright cosmic explosions. By studying D6C2NM, scientists gather valuable information about these extraordinary events. Analyzing ultraviolet light from the supernova helps determine the amount of matter created during the explosion and the temperature at which it occurred. This data is crucial for understanding the conditions leading to such immense energy release. The study of D6C2NM opens a new window into superluminous supernovae, helping scientists build a comprehensive picture of how they occur. Each discovery brings us closer to unlocking the secrets of these powerful cosmic events. The discovery of D6C2NM has also spurred scientists to search for more distant supernovae, hoping to find more examples and further enhance their understanding. Finding these distant supernovae is challenging, requiring advanced technology and sophisticated techniques. Telescopes must be finely tuned to detect faint signals from such distant objects. However, the potential rewards are immense. Each discovery adds another piece to the puzzle, helping scientists unravel the universe's mysteries. Recently, astronomers have been puzzled by vacuum energy, the energy present even in the emptiest parts of space. Measuring this energy on a large scale compared to a tiny scale reveals a massive difference of 122 orders of magnitude. Some scientists propose the generalized holographic approach, suggesting that considering tiny fluctuations in the vacuum can bridge this gap. Including these fluctuations in calculations reveals our universe might resemble a black hole, where gravity is so strong that not even light can escape. This theory becomes even more intriguing with recent JWST findings. The telescope detected 6 gigantic galaxies, each up to 10 times larger than our Milky Way, appearing just 500 million years after the Big Bang. According to the Big Bang model, such galaxies shouldn't exist so early, requiring billions of years to form. These galaxies' rapid formation and massive content challenge current astronomical models, suggesting our universe might have been created by a gigantic black hole. The idea is that our universe could have evolved from a black hole in another universe. Theoretical physicists, like Nikodem Poplawski from Indiana University, propose that the Big Bang might result from a massive star collapsing into a black hole in a parent universe. In this scenario, our universe could be inside a black hole in another larger universe, with matter and energy pulled into the black hole popping out in a different place, possibly in another universe. This exit point is called a white hole, with a black hole and a white hole acting as two ends of a tunnel called a wormhole, a shortcut through space and time. Poplawski's intriguing idea suggests that a massive star collapsing into a black hole could birth a whole new universe from the white hole at the other end of the wormhole. What are your thoughts on the James Webb Space Telescope's recent discovery at the edge of the universe? Thanks for watching another episode of Space Trailway. While you are here, click the video on your screen for more quality content.